Hey, how's it going? The donk is getting out of control. Just totally out of control. Hey, good morning, D Stratus. Good morning, Ando Bear, Plammer, that guy who stinks, Alex Cart. Should we control the donk? Hey, that's what we have set out to do. Hey, good afternoon, Mike. Ando says never control the donk. Hello, H Swan. Happy Wednesday to all of you. Hello, Nookus. Guys, spring is really upon us. There are things blooming outside. I was sneezing a lot this morning. Spring is here. Donk is love, donk is life. It's also sad and cold and rainy today. That's true. Yesterday was so nice and sunny. Today it's cold and rainy. But that makes me... There's a good way to think about this though. That rain is going to nourish all the plants that are going to explode like crazy this spring. April showers bring May flowers. Ando says I got taught to play football yesterday. Are we talking American football? Pika says, although I still had to open my window this morning because my cat was getting mad she couldn't see the birds. I love hearing the birds in the morning. American football. Okay, nice. Rain is good, so it washes all the salt away so the fun cars can come out. And motorcycles, as the weather improves, we're seeing more motorcycles. I would love to get a motorcycle, but I'm also scared to death of wiping out. So I don't think I'm gonna get a bike. The birds always wake me up. It's not a bad way to wake up. All right, you guys ready? I'd be scared of other people if I had a motorcycle. Yeah. I saw a man hit a deer with a motorcycle. Good grief. Guys, I want to add, we're gonna keep working on this code. We started this on Monday. And I want to add some features. Let's talk about the features that I want to add today. Okay, not necessarily in this order, but I want to add the ramp response. We've looked at how these controllers perform if you give them a step reference. What about a ramp? Okay, so we're going to add in the ramp response. We're going to talk about that. I want to talk about calculating the control signal. U. So we've been plotting the output Y But it's important to also keep track of the control signal. And the reason is, some of these controllers we make, they might... So like if I plot the controller versus time, they might, I don't know, it might give you a control signal that does like this. And you have to be careful because you need to look at the amplitude of this control signal and ask yourself, does this amplitude exceed my hardware limitations? This is important because, so if you've looked at Project 1, we're controlling a DC motor and we only have a 6-volt power supply. So what's going to happen in real life if, like let's say this amplitude was actually like 9 volts or something. What's going to happen in real life is up until you get to, well, let's say 6 volts is right here. This is the actual limit of the hardware. Everything's going to be working fine until you get here, and then you're not going to actually be able to make up this difference in real life. And so this is called saturation right here. When you saturate the input, it can't go any higher. And the dynamics that happen once this saturation occurs, it's going to be totally different than what you simulated. So you're in uncharted territory once you start saturating this control input, because it's not going to match your simulations. Your simulations think that, oh, everything's fine, I can do this. Actually, I guess you could build that saturation into the simulation and see what really happens. But this is one of the reasons we want to keep track of the control signal. Everything might look good in simulation, but once it comes to your hardware, who knows? Okay, so that's the second feature we're going to add today. Another feature I want to add is visualizing closed loop pole options. The extra 3 volts is saturation. Pika asks, saturation in general just means you've reached the limit of what your controller can actually provide. So saturation is just once you hit the 6 volts. Okay, so last time what we did is we made 10 different controllers, and we one by one we said like, hey, what are the closed loop poles? It's going to be more efficient to plot a bunch of these poles at once as a function of some of the control parameters. It'll just make it more efficient for when we look at different options and narrow down our choices. Okay, there might be another thing that I wanted to do that I'm forgetting about. But we'll start with these 3 things for now. How about we start with calculating the control signal? Let's go back to the code. If you are behind in the code, you can always come back to the video from Monday. Jack says, in terms of saturation, is there any difference between 9 and 6.1 volts? I see what you're saying. I think that like if I saturate by a little bit, is that just as detrimental as saturating by a lot? Like, I guess they're kind of the same in that if you run into a situation where you're trying to generate something above what the hardware actually makes, the hardware is just going to stay at 6. There's nothing else it can give. So in either case, it's no bueno. I mean, the more that you saturate, the bigger the difference is going to be between your simulation and what happened in real life. So maybe saturating by a lot is worse. Okay, something that you should add to this code right away. Because I noticed, actually maybe it'll happen right here. When I ran it, oh, never mind, it worked. But if you run it, it might give you an error because it might have some variables stored from a previous program. So I think it's good practice to always throw this at the top of your code. If you're getting an error you can't understand, oh yeah, CLC, that's a good one too. That clears the screen. So it just clears everything up every time you run it. Okay, so the first thing we're gonna do is we're gonna see what our control signal is. I think the fifth control, we made 10 different controllers and the fifth one looked pretty good. I always add a cleanup section to my codes, says Locus. I think that's a fantastic thing to always remember to do. All right, so this was controller 5 of 10. And remember, our goal was to get like 16% overshoot, this is very close. And like a settling time of 2 seconds. We did a very good job. And we want 0 steady state error. So we satisfy that because here's our reference and we made it exactly to our reference. Easy 8 says the all and clear all is redundant, but still works. Let's see. Using clear all usually decreases code performance and is often unnecessary. Wait, do you just use clear? Wait, what is... Oh, so you just have to do clear? You don't have to do clear all? If you want, by the way, you can clear specific variables by like putting the variable right after. I forget if you separate it with like, I forget exactly the syntax, but you can also be specific about which you clear. I didn't know that, Easy 8. I'm just gonna use clear. Boom. You better be right though. I'm gonna be so mad. That guy who stinks says, dang, yet another thing I've been doing that's wasting time. Okay, so let's go back over here really quick. We're gonna talk about calculating the control signal. And here's how I'm gonna explain it. We have our feedback loop. This is not, what I'm showing you is not the only way to do this. Close and close all, I'm not sure. That might be redundant as well. Okay, so I have my reference, I add that. This is my output, I subtract that at the feedback. Here's my error. Here's my control signal U. So we want the control signal. So this is the way we're gonna do it, or the way I do it. This isn't the only way. You could say that the control signal is the controller operating on the error signal. So the error signal is the difference between the reference and the measured output. Just tested, think it is also redundant. So you're saying I don't need an all? Our collective efficiency is off the charts now. Okay, now this output is the plant operating on the control input. So let's put that in here. So R of Z minus the plant G operating on the control input U. Now, you lied. Not cool. Now, this is going to allow me to make a transfer function. People who cut corners once, they never just do it once. All right, let's bring this U term over to the left-hand side. So I'm going to have 1 plus g of z times d of z times u is equal to d of z acting on our reference signal r. And now I'm going to make a beautiful transfer function. U of z is d of z divided by 1 plus g of z d of z operating on the reference signal. And what I'm going to call this transfer function right here, I'm going to call this the closed loop control signal transfer function. If you cut enough corners, you end up with a circle. I see what you did there. Now, what you can do is whatever reference you're using, whether it's a step reference or a ramp reference, you can feed that to this transfer function, and it's going to automatically determine what the control signal is. I think that's very cool because this is a targeted transfer function that gives you this signal out of the feedback loop. I haven't a clue what's going on, but I'll sure act like I do. Naruto Uzumaki. Hey, thanks. Is that from the Naruto show? I haven't watched any episodes, but I've thought about it. Let's put this transfer function into our code. Let's go. We have this loop. Praying we can call this function clonk. Okay, what we're gonna do, we're going to make... Did you have to watch it? It's so good. All right. Isn't there like a million episodes though? That's really intimidating to me. All right, closed loop control signal transfer function. Every main character is horrible and annoying. Good grief. Okay, I'm gonna call this G U closed loop or Guckle. Okay, so what this is gonna be, it's D glunk. So it's D divided by 1 plus G times D. And I'm doing D in because, remember, we're testing a bunch of different controllers where N goes from 1 to the number of controllers we want to make. I'm making 10 right now. So we're going to have to make a different Guckle for every controller. Okay, 1 plus G times D N. All right. Okay. What about Dragon Ball Z? I love that one. Now let's go down here. This is where we got the step response. This is the output of closed loop system. Let's also look at the control input. So I'm going to provide a step to, oh wait, guys, up here, make sure you also add, so line 43. Yeah, Kate, thank you. Thank you, Kate. We need that. So I need Guckle in. Full Metal Alchemist, I loved. I keep looking for something like Full Metal, and I don't know what that is. Maybe you guys know. Okay, so we're gonna do this step. Let's do it for the 5th controller, because this is the one we thought looked pretty good. So this is control signal I'm going to add a comment here. What are you making? Just a gist of this project. We're making a control system. And actually, I haven't specified physically what the system is. I'm not sure physically what it represents, but we're trying to control it. We're trying to make it do what we want to do. And we're looking at a bunch of different options to decide which one is best. All right, so let's make a plot of the control signal. But what I'm going to do is I'm going to organize this a little bit differently. I want to make subplots. You've probably done this before. When you do subplot, you can make a couple plots stacked on top of each other. So this is going to make a 2x1 grid. And the second plot, so the bottom one in this grid, is going to be our output. But I want to do, we're going to add another subplot, and this is going to be 2, 1, 1. It'll be the first plot of the 2x1 grid. And we're going to make this be the control signal. I'm going to remove this part of the plot because this was plotting the reference signal, which really isn't relevant to this. Okay, let's change the Y label on this one because this one is the control signal. And maybe on this one, I'll specify that the label on this one is the output. All right, so now you'll see what happens. How about we just run this and then we'll come back if we need to. Okay, so you see the subplot 211, it made a 2x1 collection of plots. And the first of the 2x1 is the control signal. And the second is the output. Let's zoom in a little bit more. Now, let's do this. This is what I'm talking about when you need to be careful. So this top one is the control signal. And you see it has the largest amplitude right at the very beginning. It has an amplitude of, I don't know, around 12 or something. Depending on your hardware, you may find that like, hey, I can only output 5 volts or whatever the control signal is. And this is going to be requesting 13 volts. Well, you know right away that this controller is not going to behave in real life like it does in this simulation. What I mean is like right when you start the controller, instead of giving 12, it's just going to give the max that it can, which might be 5 or 6. And when you look at the output, it's going to move up much slower because it can't give as much juice. Okay, so that's a practical example. Okay, so this is how we can calculate the control input and see what it looks like. How about we look at some other controllers? Because I remember there were some other interesting options. Like, how about the 6th one? Can you show me the plot lines again? You mean these lines of code? Oh, you know what I'm going to add? I like to add a grid to my plots. So I'm going to add a grid to the first plot. I'll also add a grid to the second plot. And it doesn't really matter. I don't need 2 commas though. You can just kind of tack this on wherever. So this will make a grid for the top and bottom. Okay, let's look at the 6th controller. Notice this control signal uses a little less amplitude. It starts at 10 instead of 15. What about the 7th? So now it starts even lower. It starts at like 8, but it actually dips below 0 and then settles back to 0. You like grid minor? Wait, do I have to do grid on and then grid minor? Wait, Plammer, are you joking? Are you trolling me? Another pro tip. Wait, so I don't have to do grid on, I can just do grid minor? Let's try this. If they're lying, they're banned from the channel forever. Oh, nice. I like this. That looks a lot better. Okay, thank you. I'm starting to think my whole life has been a lie. Me too. I didn't know this. I've been doing this other stuff for years. I've been doing it inefficiently. Okay, guys, let's go back. So we have added the control input. Now let's go back to our agenda. We need to look at the ramp response. So we've seen how these controllers respond to a step. We need to look at how it responds to a ramp. This is not as straightforward in MATLAB because we've just been using the step command, right? There's no analogous ramp command in MATLAB. So you have to do a little bit of a workaround. Antonio says if you do both, it adds the major grid lines too. Wow. We're gonna add so many grid lines. Okay, what I want to show you. Okay, so let's look at our controller this way. You have a reference signal. We have our closed loop transfer function. And then we have our output y. Jack, don't worry, we're gonna add another plot. All right, so let's talk about a step reference. In the time domain, like the reference at step k is going to be 1 if k is greater than or equal to 0, and it's 0 if k is less than 0. So it's just a step starting at k equals 0. If you take the z transform of this, well, that becomes what we call r of z. But for the unit step reference, the z transform is z over z minus 1. You'll see why I'm doing this in a second. This is building towards the ramp and how we're going to simulate it in MATLAB. So when we simulate the step response in MATLAB, we're saying our output is the closed loop transfer function operating on the reference, whatever it might be. So in our case, for a step, it's the closed loop transfer function operating on z over z minus 1. All right, so when we do the step command, it runs this. It simulates it. What about the ramp? Let's talk about a unit ramp reference. In this case, the reference at step k is equal to k times your sampling period, capital T. But this is for k greater than or equal to 0, and it's 0 for k less than 0. So if you were to plot this over time, this is why we call it a ramp. It just does this. And the slope of this line is 1. That's why we call it the unit ramp. Okay, if you take the z transform of the ramp, which once again we'll call it r of z, because now it's in the z domain, it's going to be your sampling period t times z over z minus 1 squared. I'm going to try to zoom out a little. Oopsies. Compare this to the step. And you'll see they look pretty similar. Wouldn't the slope be t? Okay. No, that's a very good point, Jimolino. The slope is 1 if we plot this reference as a function of time. If we were to plot it instead as a function of k, then like when k equals 1, it'll be equal to t. And when k equals 2, it's going to be equal to 2t. And you're right. In this case, the slope is equal to t. But I was just saying, like, as a function of time, it's just going to go up by 1 every second. And that's why we call it the unit ramp. Okay. I'm going to break this up. So this is the unit step, z over z minus 1. If I multiply that by t over z minus 1, then it's the same thing. The reason I'm doing this is because now what I can do is I can use the step command in MATLAB to give me like this part of the reference. Okay, let me show you what I want to do. And I think I learned this trick from Dr. Mook, actually, in dynamic systems. So maybe you guys know this trick already. Okay, so the output is the closed loop times the reference. So this is, let's plug in the reference. And actually I'm going to kind of like rearrange this, but I'm going to call it like t over z minus 1 times z over z minus 1. So this is a ramp reference right here. But look what I can do. What I can do in MATLAB is I could make a new transfer function that's equal to this. So it kind of like absorbs part of this ramp. And then I can apply a step input to this modified transfer function. You see what I'm doing? It's kind of like I took part of the reference and I had the transfer function soak it up so that then I could apply a step to that transfer function. So let's make a new name for this one. I'm just going to call this G closed loop like ramp. And then I'm going to get the step response of that. And that'll actually be the ramp response of the closed loop system. Does that make sense? It's a nice little trick. All right, let's come back over here. Let's add this in here. Okay, so we're gonna add something in here. Closed loop transfer function for calculating ramp response. Let's call this G closed loop ramp. So it's G closed loop G closed loop times t over z minus 1. So we just have to multiply this by a transfer function that is t over z minus 1. So remember, you have numerator, denominator, and sampling period. There's 3 arguments for the transfer function. So the numerator is just t, and then the denominator was z minus 1. So z minus 1. Beautiful. Now what we're going to do let's go down here and make a ramp response portion of our code. Ramp response. Let's call y ramp. So now we're going to take the step response of our rampified closed loop transfer function. How do we do number 7? Because that's what we've been looking at for the other ones. And we're going to use the same syntax like we did up here. So this is the ramp responsive closed loop system. And now I'm making another figure jack. Okay, here we go. Plot. I'm going to take, I'm going to recycle this stuff when we were plotting y earlier. But I'm just going to change y in here to y ramp. And the reference, this is just a unit ramp reference. So it's just going to be t over time. No, I know, Jack. I know you were joking. I'm just giving you a hard time. Okay. Let's run this. Oh, whoa. Does it look like we're getting farther away? I think it should settle to a finite error in here. Let's simulate it a little bit longer, and I think we'll see that it doesn't get farther away from the reference. Let's simulate up to like 8 times the settling time. So we're going to simulate a little bit longer. Wait, is it still getting farther away? It isn't, right? Let's make it 20 times. And zooming in out here. Yeah, it looks like it's settled in to this steady state error for a ramp. But you see it lags behind a little bit. Let's try the 5th controller, which we really liked for the step response, but how does it look for the ramp? Does that mean it's type 1? Yes. You could probably plot T, Y. Oh, this one is much better. And I'm actually gonna reduce the simulation time just to like twice. No, let's make it 4 times the settling time. Oh man, this one looks worlds better. You could probably just plot T minus Y. Oh, that's good. We could also plot, so we made like a control signal transfer function. We could put in the closed loop error transfer function, which you've done for the homework. That's going to be the same thing that gives you back the error. Okay, so Now we have the ramp response. Oh, we can get the control signal for the ramp response. Let's do that really quick before we move on. So this was our closed loop transfer function. But what does the control signal look like for a ramp? We need to add the same kind of modification we added here if we want to use the step command. So what I'm going to do, I'm going to make like a ramp modified version of this. So I'm using the same trick that I used for the other transfer function. So I'm taking the closed loop control signal transfer function, multiplying it by this, and then when I apply a step to this, it'll be as if I was applying a ramp. Let's do that. Okay, so I'm going to go here. I'm going to call this U ramp, and it's going to be GU closed loop ramp. I could make this a subplot again. Just really quick. I gotta make this 2. So this is U ramp. Let's run this. Hopefully that works. So this is our control signal. It looks like a step response itself. And notice, to keep increasing the output over time, the control signal needs to remain constant for this particular system. For other systems, the control signal would have to increase as this increases, but not in this case. Okay? Making sense? Let's talk about another feature that I wanted to add. Okay, visualizing the closed loop poll options. So far, we've been looking at everything one by one, and that's just not the most efficient way. It's not. And we're improving our efficiency today. So how about, like right after this for loop, we add a little section. Visualizing closed loop polls. Now, because we're using the root locus method, we know where 2 of our polls are going to be. They're going to be located at Z star, the desired closed loop poll location. But there's a third poll that we have to keep track of. And that's kind of the thing we need to monitor here. Okay, let us do this. We made a variable closed loop polls. So these are the closed loop polls for every controller. How about we just look at that really quick? Okay, so each column is the closed loop poll for that controller. And if you look at every column, they share 2 polls in common. These complex conjugate pairs, the 0.5158, they're in every column. The order is like kind of different for every option. Okay, so one way we can plot this. Here's one thing we can do. Wait, I want to go up here. Closed loop. Wait, how do I want to call this closed loop polls real. I'm going to get the real part out of all of those. And you can just use the real command. Close loop poles. That'll grab the real part. And I also want to do the imaginary. We're going to start with this. And then we're going to make a figure. And we're going to plot all of these poles at once. And this is just what we're going to start with. I don't think it's going to be the most useful figure. We're going to work our way towards it though. Let's use X's because poles are usually indicated with X. And let's make these, let's increase the marker size. I don't know, like, I need to move this over here. And this here. I don't know, maybe like 16 or something. And then I'm gonna do grid minor. Let's try it. Actually, I don't need a column here. Closed loop, so we'll do the real part, the imaginary part. So this is gonna show the poles in the complex plane. I don't need to run the whole code. I'm just gonna evaluate this section. Okay, so what's going on here? Remember, for every controller, these two complex conjugate poles are going to be the same. So the only thing that's changing between these controllers is the third closed loop pole, which is moving along the real axis here. And if we were fancy, we would superimpose the unit circle on this so that it'd be real easy to dictate or to figure out stability. I mean, if you look at the x-axis, you can see that this route is definitely unstable because it's a distance of like 2.3 from the origin. So it's not inside the unit circle. And all of these routes over here are also not inside the unit circle because they have a magnitude greater than 1. So just visualizing this right away, it tells us that only these couple controllers in the middle are stable. Ooh. Well, what if I do this? Z-grid. And what if I do this? I think, because I want to make it like, let's try this. Z-grid axis equal. Let's try that. Oh, buddy. Brilliant. Brilliant. But let's change the color of these because they're a little bit hard to see. So we'll also pump up the line width here. You can use the line width command and make it like, I don't know, 3. That'll make all the X's thicker and it'll make them red. And then I'm going to evaluate these lines again. Aha! Okay, so we know that this controller's stable, this one, this one, this one, this one, this one. This one is really on the negative real axis in a place we don't like. So we probably going to throw that out. 1, 2, 3, 4. Actually, I think this is controller 1. This is controller 2, 3, 4, and 5. And 5 is the one we like the best. 6, 7, 8 is unstable. 9 is unstable. 10 is unstable. Okay. So I think this is a somewhat useful plot to do because it just quickly lets you know, okay, some of my controllers are stable. We're okay. I want to show you another plot. So this plot also shows you that it's the real part of the roots that that matter because it's this third root on the real axis that we're really tracking here because all of the controllers share those complex conjugate roots in common, so we don't really have to worry about them. So I'm going to make a different figure. And this one, I'm just going to plot the real part of the roots, but I'm going to do it as a function of controller parameters. The parameter that I'm going to go with, let's see. If you remember how we started this code, we picked some angles for the 0 over a certain range. And then everything followed from that. So it's kind of the location of the 0 and the angle it makes that started this whole design process. So how about, because it starts here, I plot the poles as a function of this 0 location. So actually I'm going to do Z1 on this axis, on the horizontal axis, and then I'm going to do the real part of the poles. Let me check something really quick though to see what is the size of that. 3 by 10. I think I have to take the transpose of this so it's a 10 by 3 to make this work the way I want to. To take the transpose, we have to put a little apostrophe. Let's do this still. Like I'll plot them with X's. But I'm going to change the X label so this makes a little more sense. So the horizontal axis is the location of the 0. All right. And then the Y label is real part of closed loop poles. Let's do this. Oh, let's turn on the grid as well. This will make it a little better. And I'm going to use grid minor. Okay. On the horizontal axis is the location of our 0 for the controller. The vertical axis is where our poles are. So let's, for example, let's look at this value of Z over here. It looks like it's around 0.3. So we have one pole, and this is the real part of the closed loop pole. This is at negative 2.3, okay? The other real part corresponds to the complex conjugate pair. So there's actually 2 roots that have this real part. So that's why for each value of Z, you only see 2 X's visually. Because really, 2 of them are on top of each other here, and there's 3. So what we're tracking is the real part of that 3rd pole. And what I can quickly do is like zoom in here. Will a type 2 system have a greater control effort than a type 1 system if there's a ramp response? Not necessarily. Not necessarily. What you can do is, I know that the real part of the root has to be between 1 and -1, so I could just like truncate this plot. I could zoom in between the 1 and -1, and these will be my stable controllers. Okay, so I know that the location of my 0 has to be between whatever this far left limit is, around 0. Well, I guess we can make this a little more precise. Like, it should be like between 0.3 and 1.6. And you can narrow this down even more because like this pole's on the negative real axis. So maybe I want to limit even to here. So this is like, if I want my real part of that third pole to be somewhere in here. Actually, this real part is like 0.8, which is pretty far from the origin. So this controller is probably going to dominate our target poles, and it's going to be slower than we want. So maybe I can actually truncate a little further. And so why I like to do a plot like this is I can say, hey, I want controllers that have a 0 between 0.48 and 0.68. And what you can do is you can go back to your code and you can make a bunch of controllers in between here. So it's kind of like you zoom in, and maybe I make 10 new controllers within this range. And then I see if I find one that I like even better. So maybe we can even do that really quick. I want between 0.48 and 0.68 for my 0. Let's see. Oh, the way I've set it up now, we'd have to actually modify it a little bit, because I'm using the angle here. So maybe it'd be better to plot the closed loop poles as a function of angle, because then I can just specify a tighter angle here. I'm going to do that really quick. I know we're running over time. Okay, instead of plotting Z1 here, I'm going to try angle Z1. And I'll just put like angle here instead. Let's make another figure. Let's just try this out. Okay. And maybe I'm going to go like in here. And this is in radians right here. So maybe I'm going to try angles just from 1.3 to 1.9 radians. Huh. I'm going to copy this. So I'm going to change my minimum to maximum. My minimum, what did I say? Let's make it 1.2. My maximum, I'll make it 1.9. And then I can run this code again. And now, like, the indices are going to mean different things. It's going to be totally different controllers because I'm trying a totally different range. But all of the controllers in this case should be pretty good. Okay, a little trick. I don't want to run these simulations down here yet. So what you can do, you can put a pause point in your code by pressing keyboard or typing keyboard. And the code will run up to this point and then it'll stop. So I'm going to run this. And now it's just showing 10 versions of the controller over that tighter range. Oh, sad. I just ran it all. Well, that's okay if you ran it all. It'll just make some plots. And looking at this, like, I might want to tighten this up even more. Because, look, I have some roots on the negative real axis. So maybe my... but you see my point? Like, you can just keep tightening it up so that that real part of the root falls into a region that you like. And this is a way of just iterating pretty quickly and getting very close to where you want to be. If you want, so this green arrow, that just tells you you're in debug mode now. If you want to quit debug mode, and it'll have this K here for keyboard, you can say db quit, and it'll just exit debug mode. And then you're back to normal. But I use that command all the time. It's super great for debugging code as well. Yeah, if we run this lower stuff, it'll do the 5th controller from that limited set. And all of those controllers are going to be pretty good. Okay. So, in review, we looked at how to get the control signal. You can say db continue to terminate debug and keep running the code. Yes. Oh, if you click the lines next to the line number, it also adds a debug point. Oh, I see. So instead of pressing keyboard, you can just click right here, and that serves the same function. Yeah, so now it'll stop right here. Hopefully. Yeah, okay. And then it's saying like, hey, we stopped here. So if I want to continue running the code from here, like you can see I'm in debug mode. Like Kate was saying, you can do db continue, db cont, and it'll finish the code and exit debug mode. So it's a real nice trick to be able to pause your code. So when you're doing project 1 and you're trying to find your best controller, this is going to be something you want to try to iterate through the root locus design. You're going to have that extra layer in the project of picking your closed loop poles. Like for this example, well, I mean, this code kind of starts when you already know what Z star is. For project 1, there's a range of Z stars that you could have. And so what you might want to do is you pick a Z star and you go through this iteration and you're like, I didn't really find one I liked. Well, you can find another Z star and try this whole process again. And once you have the code in place, it's really not a lot of work to iterate. You just need this structure. Could you go back to where GU closed loop ramp was defined? Sure. So I just take the original closed loop, I multiply it by this piece, and this is kind of like a piece of the ramp reference that I'm absorbing into the other. How much handwritten work would you like for the project? Can it be like 95% MATLAB? That's okay, but what I want you to do is can you please scroll through the code really quick? My code is a disaster. Yeah, we can take it. I'll scroll as I talk. So to answer Liam's question, I would think of this as like a short lab report where you say like, hey, kind of like how I build my homework solutions. Like you start with like, hey, this is how I'm doing the problem. These are the steps. Here's the result. Here's the code. But don't just turn in a MATLAB code. That is not... Think of this as a report that you're giving to a boss to like convince them that like, hey, this is the controller we should be using because I've gone through these steps and I'm convinced that this is going to work well. It's always good to practice that because it gets easier and easier. Ando Bear can tell you, he just interviewed for a controls job. I think it's important, just as important, the technical skill you have, it's just as important to be able to communicate it clearly. Because when you're like interviewing or when you're in the workplace, you have to be able to be like, hey, this is what we're doing. This is why. You don't just give somebody a MATLAB code and say, hey, that's it. No. We're still doing the slow scroll. Did you guys get what you needed? This is all just plotting, copying and pasting. Huh. You know, guys, I think we're just about wrapped up with lectures on root locus. Engineering with communication skills? What? Luckily for electrical controls engineers, we don't use MATLAB too much. I would say anybody using digital controls needs coding. If you're going to do a control system design like this using root locus, if you do this by hand, actually, I don't know how you can do this by hand. It wouldn't be efficient. It'd be a terrible idea. So, I mean, you could do this in Python, but I don't know what you mean when you say electrical engineers don't do this, because anybody who does a digital control system has to do this, or there's just no way. Is that controls engineer in the job title? Thinking of how to find some. Andobear says, still waiting for my decision. My friends who works there says they have a lot of applications, but that they did like me. Okay, good. They simply know the correct Z star by instinct. Yeah, I'm sure. I'm sure. Like, I know a lot of controls engineers in industry, you might have some existing hardware with PID gains that you want to tweak, and maybe, like, by experience in the particular company, they know, like, hey, we want a proportional gain somewhere around here, derivative gain here. But what we're learning is, how do you go from beginning to end, justifying your control decisions, PLCs and such? Yeah, sure. I mean, but what I'm saying is, even if you're doing something like that and you're designing something with this level of detail, there's no way around this. If you want to be a controls engineer like this, you have to be familiar with programming tools. MATLAB and Python are two sides of the same stolen C++ library. Sure. As long as you have some tool that you're comfortable with that allows you to quickly automate, look at different things, then you're good. Just started learning Python for fun. I need to get back into Python. That's something that I really want to do because it's super valuable. I stumbled upon, I don't know why people hate coding. It makes life easier. Like, I get that coding is difficult when you first start. Like anything. It's a language. But the more you use it, the more comfortable you get, and it makes your life easier. Yes. D-Stratus says, I'm a little confused on this constraint. The input voltage cannot exceed... Okay, D-Stratus, what that constraint means is... The power source for this motor, it can only output 6 volts. Well, plus or minus 6. Because I can change the polarity of the voltage. So what I'm saying is, if you make a controller and you simulate it, and it's saying like, hey, we need 8 volts, then I'm saying don't use, like, that's not a valid controller because I can't actually use 8 volts in real life. So I want you to design a controller that behaves in simulation, hopefully close to how it's going to behave in real life. And so you have to be within the power limits there. Mark says, I don't think there's many engineering jobs in the future that won't need some kind of coding. That's exactly right. That's exactly right. Galapagos says, do you know if this class counts for controls, dynamics, mechatronics graduate track? I believe they're adding it to the suggested class list. It should. It should count on that track. So the overshoot has to be less than or equal to 6 volts. Yes, for the control input, you're right. You're right. There's something I saw the other day, which I want to try out. Have you guys heard of Collaboratory? Hey, see you, that guy who stinks. I had not heard of this. But what it is, it's like a Word document, but so you can, like, I don't know, like any Google Doc, you can add like bullets and like stuff. Cool. But then you can add LaTeX code, so that's how I make pretty equations and stuff. But you can also add Python in here. So like, I don't know, how do I do this? Let's add a code block. Actually, I don't remember like any Python right now. You should watch Hunter x Hunter. Ooh, I started that actually. So this is not a valid Python code. I think they have some examples here. Is there some examples? Video interpolation. Run in Google Colab. So the cool, like, so this document that I'm reading, they made it in Colab. So it's like you have text, and then you can also add Python code in here, and I can like run the Python code. Wait, how does this? Okay, so I'm a newbie. I don't know how this works. But like, oh, One Punch Man, I love that. Is there gonna be a season 3? Like the code we made today, I think you could build it in Python in this environment. And what I can do, like, this is Google Sheets. So like, I mean, this is on Google Drive, so I can like, I would be able to share it with you. You also love Mob Psycho, 10 out of 10. Hero Academia. I watched like 1 or 2 episodes of that. My cousin said it's very, very good. Hero Academia gets annoying. I just want another. I want another Full Metal Alchemist Brotherhood. Jujutsu Kaisen. I don't know that one. Cowboy Bebop. I really liked. Oh my gosh, One Piece is... There's just so many episodes. Like, when I look at a show like that, it's just like, oh man. Isn't it the same thing with Naruto? There's like a billion episodes. Okay, so I gotta watch Hunter x Hunter. I gotta watch My Hero Academia. Death Note. Hellsing is pretty good. Read the manga. Hunter, like I've watched, how many episodes have I watched? Maybe 7 or 8. It's taken me a little while to enjoy the characters. Like the main character is a little too chippy for me right now. You know, he's like the bright-eyed kid. Super skilled but super naive. Naruto's like 500 episodes, but I skipped all the non-canon episodes, so it's like 300. Okay. Oh, nice. Hitman Reborn is also good. Towards the end of season 1, it gets good. I'll give Hunter another try. So I've heard from multiple people that it's like it's really good. Have you met Killua? I don't know. I don't know if that sounds familiar. So, is it the... I've met that clown dude. Hey, see you Friday, Belkit. The white-haired kid. Is that the guy with the skateboard? Hisoka's the clown. Okay. I think I met that kid. Hisoka's your favorite? Or skateboarder is Killua. Okay, yeah, I met the skateboarder. That kid's pretty cool. Yeah, Hisoka, there's something going on with that person. So I think I got up to the point where they do the challenge with the cooking. Like where they have to cook a pig. Yeah, balance of funny and creepy. I can appreciate that. Are there office hours today? I have office hours for 3:34. So I won't have office hours for digital controls today. All right, everybody. I need to go eat some food and then get back into it this afternoon. We're all gonna have a good Wednesday, everybody. Hey, bye, Pika Pika. Always a pleasure. See you guys. See you, Locus. Peace, Brandon. See you guys soon.